Hi, in this series of videos we're going to examine three different approaches to multiple regression analysis: simultaneous multiple regression, stepwise multiple regression, and sequential multiple regression. Or as I like to refer to them, the good, the bad, and the ugly.
You wanted to get me killed. When'd you unload it?
Last night. You see, in this world, there's two kinds of people, my friend. Those with loaded guns, and those who dig.
To paraphrase the man with no name, in this world there are two kinds of researchers: those with theories and those who fish. Now, like I said, we're going to examine three different approaches to multiple regression. Which one you use in part reflects your answer to that question. Now, we'll start with what's called simultaneous multiple regression, or as I like to refer to it, the good. You can think of this as the Clint Eastwood of statistical approaches. Now, if you've watched previous videos, this is what we've been discussing so far. In simultaneous multiple regression, all the predictors are entered into the regression model at the same time. And you have some theoretical basis for selecting those specific variables. These are predictors of your outcome, so they might include key predictor variables you wish to study, as well as any common causes of those key predictors and your outcome. Don't forget your common causes. Now, simultaneous multiple regression definitely has a number of strengths. The results are clean and straightforward, relatively easy to interpret. And as we've seen, you can use it to predict scores for individuals based on a set of predictor variables. Now, again, got to be clear, it's not the only way that you can make predictions about individual scores. Other approaches can be used to do the same thing. And as we'll see shortly, prediction itself can be done atheoretically. Now, some say that simultaneous multiple regression is the best approach for explanatory research. That's the research that is often kind of early, that is studying the nature of some issue or phenomena and looking at ways to define or measure it. Well, sometimes simultaneous multiple regression may be the best way for that type of work, particularly if you have no idea of how different predictor variables are related to each other. But if you do have some sense or some beliefs of how your predictors influence each other, there may be a better way to do this. And some will talk about using simultaneous multiple regression or other statistical approaches as ways of determining the relative importance of variables. No, there is no statistical test for importance. Statistics can tell you how large an effect is. A statistical test can tell you how likely it is that some effect is real and not just some random chance. Statistics can't tell you whether it's important or not. Looking for importance is kind of like looking for truth.
If it's truth you're interested in, Dr. Tyree's philosophy class is right down the hall.
Importance comes down to subjective evaluations of predictors and outcomes and the values and perspectives of the audience. If I'm studying child development, a key variable or effect that is important to a geneticist may not be important to a teacher. What the teacher feels is important may not be important to specific parents. Now, like in all things, there are some downsides to simultaneous multiple regression. For example, as we've seen in previous videos, the effects will vary based on the variables that you've included or not included in your analysis. Right? That's why we need to include variables that are common causes for any key predictors in the outcome. If you include certain common causes and I don't, our results will be different. And simultaneous multiple regression does not take into consideration the causal sequential effects that one predictor may have on another predictor and thus on the outcome. Things we'll talk about shortly as indirect effects. Now, this can be a biggie. Again, as we'll see shortly, simultaneous multiple regression does not consider indirect effects. It doesn't take into consideration the possible causal relationship among the predictors in your model. So let's go through an example to illustrate how a simultaneous multiple regression works and how we should interpret the results of this type of analysis. Okay, our outcome will be grades, looking at student grades based on 4 predictors: father education, mother education, school quality, and the number of hours a child studies. For this hypothetical illustration, our sample size will be 400 students. Now remember, there are 3 key types of output that we focus on in a multiple regression analysis. First is the Anova Table, which we interpret just like an Anova. This is the overall F-test for this specific model. In this case, it tells us that with 4 and 395 degrees of freedom, our F is equal to 16.870, which is statistically significant with a p-value less than 0.001. Now, thinking back to our basketball analogy, again, this reflects whether at the end of the game did our team win or lose. This is where, in this case, we see that our team of 4 variables won, and we can reject the null hypothesis. Now, while we're down here, okay, make certain that you track and keep track of the degrees of freedom residual, because we're going to be using that later when we're testing our regression coefficients. Okay, so remember that 395. And also while we're here, let's do a quick review of some of the calculations for our F statistic. Remember, F is equal to the mean square regression divided by the mean square residual, which you may see written as MSR divided by MSE for mean squared error. The mean square error is just another way of saying mean square residual. We also saw that you can think of these as variances. So you may see this written as the S-squared regression, or the variance associated with our regression model, and the s squared residual, the remaining residual variance. But regardless of which way you say it, mathematically these all come down to the same thing. The sum of squares regression divided by the degrees of freedom regression over the sum of squares residual divided by the degrees of freedom residual. So let's quickly check the calculations just for a little practice. Okay, here's our F formula. Let's start with the sum of squares regression. Right? That's 30.499 divided by the degrees of freedom regression, which is 4. All of that is over our sums of squares residual, which is 178.522 divided by the degrees of freedom residual, or 395. This works out to our mean square regression being 30.499 divided by 4, or 7.625. And our mean square residual being 178.522 divided by 395, or 0.452. We then divide the mean square regression by the mean square residual to get our F, which is 16.870. We can then look up our p-value in Excel or a calculator or a table, and we'll see that our p is less than 0.001. We've got all that. We then write it down using proper notation as F, and then in parentheses, 4 and 395 degrees of freedom equals 16.870, with p is less than 0.001. Now, of course, if you're doing these calculations along with me, your answer will be slightly different because of rounding, and that's okay. Trust me, this works, okay? So that's the Anova Table. It tells us the overall model is statistically significant, but it doesn't tell us how large that overall effect is. For that, we need our model summary table. Now, here's a complete model summary table, but we're going to ignore those change statistics. We'll get to those later. So let's drop them, and for clarity, it's getting a little crowded on the screen. Let's slide this over and make it a little bit bigger. Okay? The model summary table tells us that our R squared is 0.146, which means that the set of 4 variables accounts for 14.6% of the variance in grades. To use our basketball analogy, you can think of this as the score for our regression model team of 4 variables. They scored 14.6% of the variance. But from the model summary table, we don't know whether that is statistically significant. That's what the Anova Table tells us. Mathematically, remember that R squared is the sum of squares regression divided by the sum of squares total, the total sum of squares. And if we go back to the Anova Table for a moment, we can see that's exactly what we find, right? The sum of squares regression of 30.499 divided by the sum of squares total, which is 209.021, equals 0.146. Cool, right? So R squared reflects the relationship between the partition sum of squares. But while we're here, we also just saw a minute ago that F is also related to the sum of squares regression and the sum of squares residual, which is just the difference between the total sum of squares and the sum of squares regression. So it may not surprise you that with a little bit of mathematical manipulation, you can show that it's also possible to calculate F based on R squared values. Let's take a quick look while we're here, right? So looking back at the model summary table with our R squared of 0.146, right? But To make this fully convincing, I'm going to take that r squared value out a couple more decimal places. Okay? If we use a value of r squared that goes out to 5 decimal places, we see that f is equal to 0.14591 divided by 4. All of that over 1 minus 0.14591 divided by 400 minus 4 minus 1, which gives us 16.870. Perfect. See how these are all related to each other. They're not just numbers appearing out of thin air. Now, with that, why don't we wrap up this video, okay? In our next video, we'll look at the regression coefficients in a simultaneous multiple regression analysis. Okay? Bye for now.